Okay, thank you for the introduction. So today I'm going to be talking to you about some of our work that we've been doing to help improve refractory alloys printability for additive manufacturing. But first, I'd like to give you a little bit of background as to why we're interested in refractory alloys. So these materials are very useful for a wide variety of environments, essentially kind of a huge variety of extreme environments is what we're kind of looking at. So anything from nuclear fusion systems to space nuclear power propulsion, or any kind of elevated temperature environments, hypersonic applications, etc. But as mentioned, these materials are very hard to fabricate. Machining is difficult. Fabrication can be really expensive, especially using traditional machining techniques, because you have a lot of waste. And so really, to help solve this problem, additive manufacturing can help us reduce the cost of fabrication by reducing the amount of waste related to creating these parts. We can obtain near net shape components, and this powder recycling allows us to help reduce the excess material that's wasted. Additionally, one major benefit that is much greater than the traditional machining techniques is the fact that we can fabricate particularly complex structures. So as you can see here, some of our previous work on ultrafine lattices, we can actually print these refractory metals into very complex structures and can actually adjust the design based on the application of interest. Additionally, you can print these types of materials in these complex geometries for things such as heat sinks, etc. But as mentioned, they are also difficult to additively manufacture. They tend to be very brittle, and so you get a lot of cracking during the fabrication process. And this is due to the high thermal gradients and residual stresses that are resulting from the additive manufacturing process. Additionally, a lot of porosity is seen, lack of fusion defects, and this is because of the fact that refractory metals have such high melting temperatures, so it's difficult to fully melt the powder and solidify the material. So we've kind of thought about how can we decrease this cracking that occurs during the production of refractory metals, but still keep the properties that we desire for these refractory materials. And one thing that we've kind of come about in the literature is using grain refinement techniques. And so a lot of the literature thus far hasn't really gone super into depth as far as a design or an approach to adding these nanoparticles. So some work has found that adding zirconium carbide and tantalum carbide to tungsten helps reduce cracking, but there's no great justification as to why they chose the compositions they did. They only looked at one composition, actually. And so our thought is that we need kind of a better way to design these refractory metals and decide how much these potential nanoparticles could be helpful. And the studies I'm talking about are cited up here. In these studies, the direct impact of the nanoparticle was particularly unclear because the nanoparticle was actually melted in both cases, and this can be caused by a low nanoparticle melting temperature compared to the base metal. Nanoparticles, because they're so small, you can get melting temperature suppression, as well as a lot of times people use overly aggressive print parameters to help get really high densities. But then what ends up happening is that you end up melting even the nanoparticles that have a higher melting temperature than your refractory metal. So as a result, you can end up having different compounds formed and get cellular structures, which tend to be very brittle and can actually be detrimental to your properties. So with this, the goal of our work is to really prevent cracking and improve printability of additively manufactured refractory metals. And we want to utilize identify and utilize specific computational tools that can help us do this. Like I said, we want to develop a rigorous approach to be able to kind of go about designing these materials and determining what effects these nanoparticles will have. And as I previously mentioned, we want to add as little additional material as possible so we can help retain those properties but help prevent cracking and actually improve mechanical properties. And really, one big question we kind of want to answer is melting good or bad? A lot of the research currently has shown a variety of effects of the nanoparticles. They can act as nucleation sites and help promote equiax grain formation during fabrication. Additionally, this helps reduce the grain size, promoting a decreased ductile to brittle transition temperature, kind of reducing that brittleness, and they also act as center Zinner pinning to help reduce grain growth during heat treatment. And all these effects can really help increase the strength, nearing values that are close to rot a lot of times. But thus far, this question of is melting good or bad? Well, there's a lot of promising results on the impact of nanoparticles, but the results can kind of vary. If you get new phases that form these cellular structures and form brittle compounds along the grain boundaries, this could potentially be bad. But if you get a secondary phase forming at the beginning of your solidification process, then these nanoparticles can actually still continue to act as nucleation sites and be really helpful. And so we're kind of trying to answer this question of how do we predict the nanoparticles' influence, and how do we determine if we're going to have melting, if we're going to have solidification at the beginning of the melt process, or if we're going to have solidification at the beginning of the solidification process, et cetera. Currently, a lot of the literature, particularly a Nature paper on AM7000 aluminum, they added some nanoparticles and actually saw an intermetallic phase form at the very beginning of solidification, and this actually acted as great grain nucleation sites. So our first thought is, how do you decide what materials to use? So we actually used nanoparticle melting temperature as a major selection criteria, and this was just to help us tease out the impact directly of the nanoparticle versus potentially the nanoparticle melting. So we looked at some of the highest melting temperature ceramics, which are carbides, borides, and oxides. And as you can see here, when you kind of take that into account, we mainly looked at the carbides because there's already a lot of oxygen in additive powder, and borides are not particularly they are particularly detrimental to nuclear applications. So we wanted to kind of keep this general to a variety of extreme environments, like I mentioned. So as you can see, if you compare the melting temperature of carbides to a lot of these refractory materials, that actually doesn't really narrow down much. But additional selection criteria that you can account for are things such as cost, database availability, further your integrated computational materials engineering designs, as well as, in our case, we were looking at neutron absorption cross-section. You can include things like oxidation, corrosion resistance, strength-to-weight ratio, et cetera, and how much these things can affect your properties. So really it depends on your application of interest, but you can use this to really narrow the playing field down. So we mainly have focused thus far on tungsten and molybdenum, and on zirconium carbide and tantalum carbide, since those are the two carbides that have higher melting temperatures than tungsten. So we looked at some initial simulations. A lot of the work thus far, we've used kind of traditional welding simulations. So you can use a variety of tools. Mainly, we've looked at using a lot of thermocalc as well as traditional weld models. So thermocalc, you can use things such as like phase diagram modeling, diffusion simulations, shield solidification simulations, which are very commonly used in additive manufacturing to predict crack susceptibility, and different things like that. And one thing that we've tried to predict is, do these nanoparticles melt or survive printing, and what methods do we use to actually predict this? So we did a little bit of phase diagram modeling first to determine whether or not we might get some unwanted phases forming. And the biggest issue, though, with this is that a lot of databases actually, for refractory metals, do not actually include oxygen. And oxygen and carbon can really have a big impact on your properties and the phases you see formed. So this makes a lot of this modeling a little bit more difficult. We also did some shell solidification simulations, and as you can see, this can help. We can use the shell solidification simulation to help predict the dendrite formation and behavior. But once again, the biggest issue with this is that if you don't have any oxygen, you actually may get different dendritic phases being formed. That said, this can give us at least an idea on an estimate on crack susceptibility. Essentially, you base your crack susceptibility on the slope at the end of the shell solidification curve. So thermocalc has a built-in crack susceptibility coefficient property modeler. This is essentially based off of the shell solidification curves. And basically the nice part about this is you can kind of get this map of how your crack susceptibility changes with the amount of zirconium and carbon. And essentially, we're looking at the diagonal on these plots. So if you kind of try to put that into a graph that makes a little bit more sense, as you can see here, there's actually 3 different approaches to use for this crack susceptibility coefficient modeler, but all of them show that they have actually a peak all around the same area. So we decided to use the approach that was the most dramatic, but also is likely the most similar to traditional shallow solidification simulations, which is the constant cooling rate approach. And with this, the way we decided which compositions to use, we just kind of picked random points along the curve, not quite random, but a few different points, trying to capture both sides of the peak as well as the peak in a couple different areas. And this is how we kind of went about designing these compositions. So I talk a little bit about our experimental methods that we used. So we used an EOS M100, and this was because it has a small build volume. It helps reduce the cost associated with fabrication, and it also helps us rapidly manufacture these materials. Essentially, it's pretty quick to clean out and different things like that. And of course, when we add these nanoparticles, the excess powder will be sieved, and so these nanoparticles may detach during powder recycling. And so we've also got a Techna plasma spherodizer in case we see this nanoparticle detachment as we move forward with our studies. To mix the nanoparticles in with our metal powder, we used an acoustic mixer, and this is a really great process. We also have a cooling fixture. This is just to help prevent overheating of the powder, and basically it keeps it nice and cool throughout the mixing process. And the nice part about this approach is that we can mix a lot of powder very quickly. Not a lot of powder, but a decent bit of powder pretty quickly, and not have any issues really with the results. We don't have any damage to the powder or anything like that. So this acoustic mixing, it really helps prevent damage and deformation to your spherical powder. A lot of studies have used mechanical alloying and then spherodization afterwards, and actually got really still non-uniform, non-spherical powder. And in our case, you can see that even after mixing a variety of compositions of zirconium carbide and molybdenum, we still have very spherical powder, no major damage to our original spherical particles. And so our side distribution does not change, which means that our optimized print parameters for the pure metal do not particularly need to change. So our hope is that we may not need spherodization after mixing unless we see this nanoparticle detachment during recycling. One issue, though, with this approach is that you actually get a saturation limit of how much of your material you can add. So we added 0.6 mol% and 1.35 mol% of zirconium carbide, and as you can see, the difference between these two is very similar. We actually started to see kind of a buildup of the zirconium carbide on the mixing vessel walls after adding 0.6 mol% zirconium carbide. So with this, you have to be careful on how much material you're actually adding and finding out that saturation limit. As you'd expect, the saturation limit depended on the nanoparticle size we used. So we used 3 different sizes of zirconium carbide, and we were able to get a lot more coverage of the zirconium of the molybdenum powder with the zirconium carbide as we decreased the nanoparticle size, as you can see kind of in this EDS image. But one thing to note is that not all nanopowders behave similarly. We tried this with tantalum carbide, and the tantalum carbide was a lot more agglomerated and stuck together, and so what ended up happening is we didn't get quite nice uniform distribution, and so we're still trying to figure out the best way to kind of approach adding these different nanoparticles. Do we need to maybe mix for longer, or do we need to pre-sieve the tantalum carbide powder to make sure that it is a smaller size distribution so it actually attaches to our molybdenum powder? From there, we did a bit of print parameter optimization on the pure molybdenum using these kinds of specimens, and this helps with rapid development. And as you can see, once we actually did this this print parameter optimization, we got pretty good results for the pure molybdenum. We previously had a cooperative agreement, or we worked with EOS previously, and they helped us develop good print parameters for molybdenum, but they actually had a different particle size distribution. So with this, when we tried to use their parameters, we actually got pretty poor results. But it gave us a good starting point for our parameter development. So I'm just going to talk a little bit about some of our initial results so far. So when we added these different amounts of zirconium carbide to molybdenum, you can see that the highest amount of porosity was where the crack susceptibility should be highest. And so this kind of is a bit promising as far as using crack susceptibility to predict some of our results. One thing to note, I just wanted to point out, is that like I said, we had this caking, so the 0.6% and the 1.35% have pretty similar amounts of zirconium carbide in it. And so when you add that to the list, they look very similar. If you take the densities, you can see that as the crack susceptibility is highest, our densities tend to be the lowest. Although we were not able to actually achieve a density that was as high as pure molybdenum, but we have seen some promising results. One thing to note is that we used all of the moly optimized parameters, and so because we've got these nanoparticles added to the molybdenum powder, this is actually going to reduce our laser absorption, and so we need to do some parameter optimization for adding these nanoparticles. So it's kind of one of our initial questions was, can we use the same print parameters as pure molybdenum or not? And the answer is no. Additionally, we plan to do some mechanical testing to look at the benefits of these nanoparticles on mechanical properties, if anything. The biggest thing that we found, though, is that adding these nanoparticles actually helped reduce the grain size. So as you can see, we did as-built EBSD as well as post-HIP on the smallest amount of added zirconium carbide. And as you can see here, the grain size is much smaller than even the as-built pure molybdenum. And so this is promising because not only are we getting these smaller grains during fabrication, so even though we do see some porosity, we probably are reducing our actual cracking, but also this reduced grain size after hipping is good because now we're not getting this large grain growth, and that should help improve our mechanical properties. So yeah, and as you can see, if we look at the densities of the post-HIP materials, they all are pretty similar to the pure molybdenum, and we had a large change in the density, which is good. These are all responding to HIP, and a lot of that excess porosity is actually being closed. And yeah, like I said, this likely will result in better mechanical properties. So yeah, just to kind of wrap this up, our goal of this work was to help reduce and prevent cracking and porosity in additively manufactured refractory materials. And we wanted to utilize computational tools to help us kind of design these materials and determine what was the best approach. We started some initial experimental validation of these simulations and identified some issues with the designs. We did a lot of pure metal print parameter optimization, and this needs to be done for the carbide materials as well. But these initial results actually show some promising trends where we don't have this large increase in grain size after hipping, which is promising. We have a major increase in the density without having large grain growth, so this is good for mechanical properties and applications. So future work is to investigate the effects of dispersibles on our mechanical properties, as well as further investigate the effects of nanoparticle size and the print parameters, and kind of extend this work to tungsten as well as moly. We're currently doing this work, but we don't have the data yet, so I didn't want to present too early results. And that being said, I just want to thank my collaborators and funders. A lot of this work was done with a NASA fellowship and done at the University of Illinois Urbana-Champaign as well as NASA Marshall. And I'd really like to thank all of my coworkers who have helped me throughout this work and have been essential for all of our discussions and things like that, particularly Fernando, Omar, and Jeff, and Torin. And with that, I'll take any questions. Thank you. And thank you for coming to my presentation.
Okay, any questions? I can run the microphone out to you. If not, oh, you've missed it. Oh no, you can. You can still take a picture of her email address if you'd like, or
Yeah, feel free to comment me or email me.
Where else can we see the research as it progresses?
So we, well, a lot of this will be presented at TMS in the future, and then of course we'll probably be publishing this in the Additive Manufacturing Journal.
Okay.
So.
And what's the ultimate goal of the whole project? So is it to have this as a commercial prospect, these materials, or? Well,
so the overall goal is just to basically be able to print these refractory metals for, so we do a lot of space nuclear power and propulsion, so some of those designs are pretty complicated, and just kind of improve the properties with some of the interactions that we see. So, but yeah, basically just make this useful all around generally to anybody who would use refractories. So.
Good. Thank you very much.
Yeah, thank you.
Thank you.
Ooh, excuse me.
Okay, we're going to move on.